Welcome back to the main room for all participants. We hope you have a nice break. And now we will move to the plenary session 2, which will be guided by Mr. Dr. Rernat Atmanto Wahyu Wibowo, Magister of Science. But before we begin the plenary session 2, I would like to read the CV of our moderator first. So, Mr. Atmanto was graduated from Technische Universität zu Brunswick, Germany, for his doctorate degree, and he is now a lecturer in Universitas 11 Maret who focused on analytical chemistry. So, for Mr. Atmanto, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. I am Atmanto Heriwibowo from Chemistry Department of Universitas 11 Maret, Surakarta, one of the member of University Consortium that hold annual conference of this GCC. On behalf of my university, I would like to thank GCC Organizing Committee for giving me a nice opportunity to accompany all participants in this afternoon plenary session in this online conference. In this session, we have two experts from the computational chemistry and also forensic and analytical chemistry. Please, I would like to introduce the first keynote speaker, Professor Dr. Zahir Ulhaq. Hello, Professor Dr. Ulhaq. Good afternoon. Nice to meet you in this occasional. I don't know whether that afternoon already or still morning.
Yeah, it's almost good afternoon.
Okay. I
11
hope.
a.m.
Okay, that's not quite nice. I hope there is no influence between Taliban or Afghanistan country to your country. Yeah, I hope so.
we can discuss on it on several hours without any conclusion. Without any conclusion.
Okay, because Indonesia is like I think all around the world it is like a hot topic. Yes. Okay, thank you, Professor. Ulhaq or Zahir Ulhaq, I don't know which one is you.
You can call me Zahir. You can call me
Zahir. Okay, okay. Thank you very much. But before we start the topic of Professor Ulhaq, please let me having time to read the CV of Professor Ulhaq. Professor Dr. Zahir Ulhaq is expert in staff in computational chemistry and laboratory at the Panswani Center of Molecular Medicine and Drug Research, Pakistan. He has some study experiences such as postdoctoral training on computational chemistry from Austria, Germany, and USA. I think that's quite nice. And also he has excellent achievement such from Fulbright Foundation from USA, of course, and then Alexander von Humboldt Stiftung from Germany. I know that I want to go there. And I want to get Stephen, but I think quite difficult. Okay, I know. And achievement, Dr. Atta Rahman Gold Medal of Chemistry from Pakistan Science Foundation, and GSP Gold Medal under 40 from Chemical Society of Pakistan, and then Research Productivity Award 2004 and 2017 from Pakistan Council of Science and Technology. And his area of interest include designing bioactive and molecular dynamic, simulation of biomolecule, including protein, and protein ligand complexes. Please, Professor Zahir Ulhaq, 40 minutes time is yours. But don't forget to the participant to write down a question to him, and you can write on the chat room. Okay, thank you.
Thank you, Professor, for your nice introduction, and I really appreciate for the organizing committee and my dear friend Poncho and Anong, so providing me good opportunity and platform to discuss my science with my good friends around the world. I don't know how many friends are, at least 164 I can see, but unfortunately I cannot see all of them. So this is the part we really miss nowadays, because now we cannot really feel our friends, and that's we are really missing. But still, at least the organizing committee provide an opportunity that we can listen each other, and maybe some good time we can see each other again. So can someone confirm me if my voice is clear and can you see my slides?
Yes, yes. We can see clearly. Thank you.
That's lovely. So in next 45 minutes, I will try to introduce lovely. So in next 45 minutes, I will try to share some of my ongoing projects, where we utilize the computational chemistry and natural products. Let me begin with the slight introduction of my institute. It is one of the finest research institute in natural product chemistry. Probably many of you already know about Professor Taur Rahman. This institute is well known from Professor Taur Rahman. This is Natural Product Institute, and we have a really a nice help of natural products. So then that was a time when we realized that this is something useful for us and we should use it smartly. And what is smartly? Smartly means now in the next phase we should try to use natural product, and not only in a random way but scientific way, so we can utilize our natural product in a much better way. Therefore, the entry of computational chemistry. So we start this field in early 2000, and now we have a very nice established lab in computational chemistry with state-of-the-art hardware and software facility. And I welcome all of my friends and my listeners that if someone would like to visit our institute, our facility, and things like that, we will be more than happy as soon as the COVID permit us. Welcome you and host you over here. So our institute is well known for the computational chemistry, natural product chemistry, and we have been state of art facility chemistry, which I am head of this department, and we have around 40 to 50 students working in this field. Next 45 minutes, I will try to cover how natural product chemistry and computational chemistry combine together to drug designing process. But before we will start with the computational chemistry, one thing that we need to understand why computational chemistry is still in fancy state. I mean, it's not that common as compared to other. Why it is so late? The simple answer, if you are talking about computational chemistry, it's already started in early 50s or 60s, I should say. But there was no much progress. The simple reason was the computer power, which is slow. But if we try to see in the last 2 or 3 decades, we can see the much difference in the computational chemistry field. Simple reason is the computational power. And you will be surprised that now the computational power is so much powerful that the competition is going on so rapidly that the computational policymakers have to decide that we have to come up with top 500 computational power. And we have to announce a list of top 500 computers twice in a year, because every 6 months the listing of the top 500 is changed. It means the rapid changes in the computer. As a result, now we can do a dream project of computer by handling as many atoms as we want. So you can see from 1993 they published the first top 500 computer, and they start publishing it twice in a year, once in a June and once in a November. And once the report comes in June, and once you are in the November, the list is already changed because the computer in next 6 months, the top 500 computers, the top computer is no more the really top, they go down third, fourth, and fifth, and the new computers come up. So we can share this. You can see this is the top 500 in June 2021. The latest report I'm sharing with you. So only alone in China is 188 top supercomputer available, and 122 belongs to USA. And then you can see the Japan, France, Germany, Netherlands. So these are the countries which have the computational power. That simply reflect, if you really would like to do some computational resources utilize, you need a computational power. And if you have a computational power, you can do state-of-the-art science in utilizing a different field, including drug design. So these are the cluster computer. Normally, these are the routine utilized for the scientific people, and a lot of people and a lot of labs are running with these facilities around the world. Not only this, so these are the computational power which people are using now. This is the cluster computer, and on the next phase we are now looking at GPU computer, which is much faster. So this is a picture I'm visiting in UK sometime. And these are the computational power. Then we plan to mimic the same computational power in our lab. Now we have pretty good facility in our lab. So These are the reasons. So if you are really interested to utilize the computer in science, you really have to come up with a powerful computer to do some dream project. Otherwise, now even the laptops are so powerful, you can do a lot of things even in your laptop, keep in mind. But if you are serious and you would like to do some state of the art science, probably you need a good computation facility. So you have to decide which kind of computation facility you can afford, and then you can move which kind of science we should include in the computer. So these are the mismatch, and you always have to decide where you have to stand and what kind of research you would like to do. And the most interesting thing is that the computational chemistry is not run by a single person. I mean, this is the most beautiful parts of my lab, I can say. So my groups already, so we don't have only from one branch of the science, so the different branches of the students are working in my lab. They are biochemists, they are organic chemists, pharmacists, biotechnology, MBBS doctor, microbiologist. So all my group is comprised of all these scientists. They are working under one roof in a one lab, and this is the beauty because there's a different brains comes in my lab, and they are working together on a different aspect of the one project. As a result, we always come up with a different and interesting results, which is quite real without it. So there's a number of techniques available in computational chemistry, and of course, in a short time we cannot discuss all of the things. But the one of the state-of-the-art facilities for microdynamic simulation. So whenever you are trying to do some computational chemistry, and but if you are talking about the virtual screening, if you're talking about the drug designing, things like that,
Hello, Professor Zahir. I think there is any interfere connection, I think so. Hello, Professor Zahir. I'm sorry for all participants. I think it is a bit disturbance of internet connection from, I don't know.
Sorry, no problem. So now can you hear me again?
Okay.
Okay.
Please continue.
Sorry for that. So we are. So if you're talking about the different types of simulation is already available, and you have to decide which kind of simulation is of use, current use in your lab. Probably Poncho is already here, and he is an expert in in the different direction of MD simulation, and what is normally what we are trying to do in our lab is a molecular dynamic simulation. Molecular mechanics will be discussed by some other my colleagues maybe. And what is simple is that if you're talking about the quantum mechanics, normally they are more hardcore chemistry and there will be more computational power, and you can deal relatively small system. But if you're talking about a biological system, they are normally the longer system. Normally we deal with more than 100,000 atoms. In this case, we prefer rather than quantum chemistry, mean classical mechanics or quantum mechanics rather than molecular mechanics. Molecular dynamic simulation, we use it. And now in the 2021, we are really lucky because we are in an age where we have more than 180,000 protein structure, well established protein structure is available. It's available for everyone, regardless you are sitting in any laboratory in the world, you can have the access of this protein. So these are the data banks. So now the data bank is really a mercy for the scientists working in any lab. Not only the protein structure, the small molecules, and so all these things are available, and they are free available access for the each and every scientist working in anywhere in the world. So in one hand, you have the database of the protein, 180,000 structure, but still they are just part of the protein structure which is already crystallized, but not all protein cannot be converted into 3D structure. And if you don't have the 3D structure, what do you think? Can you start your research without 3D structure? There's a sequence you cannot do in a lot of things. Particularly in drug designing, you need a 3D structure. So this here the computer comes and they help you to start your journey when you don't have the crystal structure from the NMR or X-ray techniques, so you can utilize the computational power to convert the 2D structure into 3D structure and then move forward. So if you go to the PDB structure, just write the theory over there and you can end up with a number of proteins. What we are talking about the natural product. So our institute is a natural, 1960s we are we are publishing a lot of natural products. We purify the compounds and unique compound, and we try to publish them along with their appropriate from last 30 years. Not only the new compound, but the new activity. So we can say the biologically active compound we are publishing. If you're talking about the approved drugs from 1982, most of them, I mean, just have a look at the idea. So approximately half of the newly approved drugs are either natural product or compound derived from the natural product. So these are the importance of natural products. And half of the drugs is already from the natural product. It means the natural product is a hub of the place where we can still work, and then we can come up with the new drugs. Now, our target? We are trying to utilize this natural product smartly by using the computational tools, so we can come up with a new entity, the new compound, new drugs. So this is the first structure probably discovered from our institute for like million. This is, you can see the picture over there. This is the godfather of our science in our institute, Salim Siddiqui. So he was working 1960 to 1990. And from 1960 to 2000, we have published, I don't know, maybe thousands of different papers with more than 40,000 natural protocols. And now what we have done recently, we convert all this compound which are published into a database. Now we have our own database, called IGCV database. This database is available as a 3D structure and 2D structure as a sample projector. And now we can use this natural product, so we can see 2,000 compounds. In next few slides, I'm trying to share some of our experience, how we converted this natural product into a doable product, how we utilize the computational chemistry to convert them to find out which compound. Previously, what we are trying to do, this is the hit and trial method. We isolate compound and then we try to test against several active targets. And if they are active, we are happy. If they are not active, probably we are wasting our compounds. But now we say no more, because natural product, they are already, we are dealing with a short of compound quantity. What we are trying to do, once we isolate them at the structure of our hand, we try to utilize the computational power to see which target is more suitable and where we should test it. And once we are really sure from the computational target techniques that these compounds should be tested against certain targets, then only we test them. And we are very lucky, and I'm really happy to share with you that our success rate is really high. I mean, more than 60% results of our theoretical results match with the experimental results. And now we only do the experiment of those compounds which comes under the umbrella of theoretical studies, and we are quite sure that these compounds should be tested, and then we test, and then we forward, and then convert it second phase, and then third phase, and the third phase. So these are the what we are doing. In one hand, we utilize our own natural product, and on the other hand, we also combine with the commercially available compounds, which is different databases which contain more than 30 to 40 millions of compounds. 40 millions of compounds free available. Everyone can download them, check them, and then only those compounds which you are interested for your target, you can purchase them. Maybe you have to purchase 5, 10, 20, 100 compounds, which is no comparison with as you compare to buy millions of compounds. You purchase a 10 compound, 20 compound after the shortlisting, and then in next few slides, I would like to emphasize what are the real techniques and procedure which we utilize for the screening procedure. Because in somehow a lot of people are doing screening, but they make a number of mistakes. As a result, finally their success rate is very low, and most of the people are disheartened, and probably this computational chemistry still cannot really help us because the success rate is not good. And I will share with you what are the drawbacks, what are the steps where you can really make a mistake in your screening procedure. As a result, your final result is not really up to the mark. For example, you are started with a structure, you download the structure from the protein data banks as you mentioned, and normally what people are doing, they download the structure of the protein and they start their visual scanning, and where they make a number of mistakes. I would like to emphasize over here that whenever you download the protein, the first step, selection of protein. If you search your query in a protein data bank, for any query, you will come up with multiple options. So probably if you write of any of the target of your own interest, you will come up with 10 or 20 or 50 different protein structure. Now this is the point, which structure I should select for my visual screening. And where you have to emphasize that what are the points I should really make sure before I'm going to select. The selection of the protein structure is very important. For instance, Maybe you have two structures, one of them they one of them they crystallize from the after mutation, and one is crystallized without mutation. So you have to read it and you have to understand if someone is a native structure or the mutated structure. If you have a mutated structure, then definitely you have to convert this mutation before you are going to test the compound. So again, you have to see, and then if the protein structure which you downloaded, they are complete and entire structure or there are some missing parts. So these are the few things. If they are missing parts, they are maybe during crystallization, they have added something unnatural. So you have to make sure that the unnatural thing should not be the part of your experiment. You have to remove them. And secondly, water molecule. So the water molecule in any protein structure, when you download from the protein data banks, normally the water molecule is not there, or maybe few water molecules. But you have to understand which water molecule is a part of the protein and which water molecule is not the real part of the protein, but they are just simply engulfed between crystallization. So you have to understand it. So these are the few things. For example, water molecule, salt, other additive, and then the complete structure, and then the refinement. So what is this refinement? And then the source. These are the few things you have to check. You have to make a checklist before you are going to select your protein structure. So once you are sure that these are the checklists, they are the confirmed, and then you can select that these are the. For example, this is the structure of cytokines we are working for a new slide I would like. So these are the active site which we are going to focus, that is IL-2 and then the IL-2 receptor. We work on it from cytokines. Basically in our lab we are working quite a lot in cytokines. So one of the target we are working from last couple of years cytokines. We decide to work on it because there are very few or almost no structure is available in this target. And this is the active site. Oh, well. It seems to be very clear. This is active side and we can straightforward our journey. But in next few slide, you can see that what are the problems. So you can see the active side is lysine, arginine. These are the active residue. These are the amino acid which our target and we have to fix it. We have to target it. So we are trying to find out some new compound which can fulfill the requirement of this residue. Seems to be very straightforward. We can move forward. And you can see that this is the structure where we would like to find out the small molecules. So you can study it in a very detail. So what are the properties of this protein? So once you download it, so again, before downloading, you try to understand the protein, and then once you decide that this is the protein we are going to decide, then you have to read it again in detail what are the requirement of this protein and how we can fulfill the requirement. If you know how we can fulfill the requirement of this target, it means you are going to be find out the proper structure for small molecules. So you can see that if these are the properties of the protein, that is a 4 alpha helix, 133 amino acid, 15.5 kilodalton, and great affinity towards alpha receptor. So these are the properties, and based on these properties, we are trying to find out. So that I'm telling you, once you download, once you read about the protein, and now we are trying to understand the protein. So you have to see these are the entire structure of the protein. What we can do, we can really focus on the active side. So this is the entire protein. Normally, if you are doing the computational power, just to reduce the computational power, we try to minimize the structure and we try to focus only at the active side. So these are the active side and these are the requirements. These are the amino acids. And in the next phase, in the next process, we will try to focus on it. And you can see easily the 3 water molecules over here. So normally it's 4 water molecules, one is over there. What are the mistakes normally computational chemists do? They remove all water molecules, and this is a serious mistake. Because keep in mind that all water molecule is not only the part, some of them are the part of the protein and they are necessary to keep over there to maintain the structure and the function of this protein. If you remove the water molecule, the structure will disturb. Structure will disturb means your function will, you lost the function. As a result, if you will screen your compound, you will never come up with the proper structure of a small molecule. So you should, if these are the part of the protein, you should keep it because they somehow involve in the bridging to maintain the entire structure of the protein. So these are the few things you have to be very sure to understand. And this is a small molecule. Then you have to prepare your small molecule. Preparation of a small molecule is also very important. You have to try to see which are the small molecules and which are the cofactor and which cofactor I should select. And then you prepare your system. You add the this is the, as I mentioned, we normally whenever we are trying to start any of project, we try to simulate our protein just to make sure that there will be no mistake over there. So we prepare a system. And so because normally if you download the protein, there in a vacuum, you again put it in the aqueous medium just to make the natural system. So mimic the nature. So whatever the protein structure we are going to work on it, it should be according to the natural protein structure. So we run a small empty simulation which gives you if there is any mistake in the protein, if any missing part of anything, any drawback of the protein structure, you can fulfill it and then you can move it to utilize it. So in our structure, you can see, so what we have done, we restock the structure just to make sure that our technique is really working fine on. So you can see this is the crystal part, this structure, and this is the redock pose, green and the. If you can see that our redocking structure is quite, and not only the one software, we utilize multiple software just to make sure that each software is reproduce our crystal structure. Because we have the complex, we need to restructure it. So normally, I will also suggest and recommend whenever you are working on any target, try to use more than one software to make sure which software is more suitable for your target. And due to different reason, different software is working. And I also discuss in detail why the different software behave differently. But in cut short, I can suggest you to whenever you are trying to start our journey, try to use more than one software in the initial level. And for example, this is a docking process over here. You can see that how this small molecule is going to during the docking simulation, how they are going to redock and find out the active site of the protein. So what we have done over there, so these are the few structures which we have published from last couple of years, maybe more than 2 or 3 decades. Multiple small molecules from the natural product, they are identified as they are different products. We are publishing the different sites. We collect all of them. So they are active immunomodulating compounds. So we publish maybe more than dozens of compounds in a different paper. What we have done, we collect all of them. So this is a small database for us. So these are the active compounds. And then we utilize this compound to start our journey. So we have the crystal structure of the target. We have the small molecules, multiple small molecules, we start our journey. For example, this is the LOX inhibitor, this is alpha glucosidase inhibitor, antibacterial activity. So these are the different compounds and they have the immunomodulatory potential. They are moderate, and then mild. We start these 3-4 compounds to utilize our screening procedure. So we can screen in 2 different ways. We start structure based and we start ligand based. So this is, you are very fortunate if you have both the information. If you have the information of the structure, small molecule, and you have the information about your protein structure based. So you can run your 2 parallel projects at a time, structure based and ligand based, and at the end you will try to compare the short state compound. If you come up with the same short compound from the 2 project, or you have a different compound, and then you compare which seems to be more accurate for our test. So what we have done, we utilize this technique. And the other technique, which is called 3D quantity structure, QSAR, quantitative structure activity relationship. So if you are lucky and you have a good sum of small molecules, let's say 40-50 compounds, then you can model a modular set. So as a result, if you have a structure activity relationship, what you can do, you can predict the activity of your non-compound before you are going to test them. So this is a very good and strong tool to give you an idea what are the possibilities that how your compound is going to behave in when we are going to experimentally. So what we have done, we also perform the 3D QSL activity, and we have a model, we ready a model, and when we shortlist the compound, we use this model to predict the activity of our compound. So again, let me repeat it. So this is a technique which allow you to predict the activity of unknown compound. So if you have a very good compound in you have a large database, good database, then your model will be strong. And if your model will be strong, then your prediction ability is very much increased. So whenever, and then it will also give you an idea which kind of modification you are supposed to do with your compound if you are going to be increased. So first you screen the compound and you can also modify the next phase. And normally there are the way that there's some colors they mentioned, the red colors normally say, so these are the place of the protein. So you can say in the entire protein, this is the place where your compound should be, some electronegative part, should be electropositive part. And if this is electronegative, electropositive, then this is, yes. So this is the steric part and this is the non-steric part. So these are the indications which give you an idea how you would like to change your compound. When you are modifying your compound, which are the things we do. So what we have done, then we perform the MD simulation of our compound, and then with the help of MD simulation, we isolate the active site of different steps. So 1 nanosecond, 2 nanosecond, 5 nanosecond, so that the active site of a compound, we have a multiple active site, and then we can run a parallel different visual screening to come up with the correct structure, because to find out the exact active structure is really hard, and you also always try to get at the final structure. So this is the structure which and we are focusing in this part. And as a result, with MD simulation, we conclude that a few amino acids are the real and crucial amino acids, which alteration of this amino acid really alters the whole complex formation. So we keep in mind that these are the amino acids. During the process of screening, we have to make sure that these amino acids should be the part of our small molecules. These are the amino acid which is going to be utilized for the screening purpose. And again, before you are going to start your small molecules, the database, you should make sure that database should be fulfilled. These are the boundaries. This is called Lipinski rules. There should not be more than 5 hydrogen bond donor, 10 hydrogen bond extra molecular mass should not be 500 Dalton. And these are the Lipinski. So you can also filter your database. For example, the commercial database, we come up 20, 30,000 billions of compounds. You can filter them as per your own need. And keep in mind, again, that Lipinski rule of 5, these are not the rules which blindly use for every target. You should always use which is called in-house, or you can say modified Lipinski rules as per your target. For example, in some target where we need a structure which should be a larger in shape, more than 500. So you can always modify. In some cases, you need more than 5 or less than 5 hydrogen atom on donor. So what I mean to say, so whenever you are going to utilize the Lipinski rule, it should be based on your target and use a modified Lipinski rules for your case. For
Jadi ini Mas ya.
It is somehow like
Oh.
internet connection break from Professor Zahir. Okay, that's quite nice. Hello, Professor Zahir. Are you already
so can
here?
you hear me? Can you hear me now?
Yes. Here.
Oh, that's lovely. Cool.
Yes.
I'm really sorry with this. This is due to the internet problem. So,
Okay. Okay.
So,
Okay, for the such country, it is common. Don't worry, Professor Zahir.
it's
Like
also
in
like
our
it.
country, yes.
So what we have done is, so we utilize this pharmacophore feature. So these are the pharmacophore. These are the part of the protein which are the responsible. So just like a key and lock model, if you're trying to find out the key for a lock, you have to provide a lock and then you can find the better key. Similarly over here, if you would like to find out which are the small compounds, so you need what are the requirement of the protein. So these are the requirement of the protein, so-called pharmacophore. So you utilize these pharmacophore metals, and then now you are ready to start your visual screening. So you start with the protein, you start with the small molecule now. So again, in this case, what we have done, so try to understand what we have done. Rather than we download one structure, one protein structure, and we run our own visual screening and one target. What we have done, we download more than one structure because all of the structures somehow they are unique from each other. So we utilize, for example, in this case, we have 4 different structures. We utilize all of them, and we run a small pilot project over here. And then once we are make sure that this pilot project is successful, then we utilize this pilot project in the large database, and then we come and shortlist the compound. So what we have done over here, we utilize this 4 structure, and then we use more than one docking software, and each software come up with a multiple options. So the software come up with a multiple option different. We use different database. So we use different, so in case of MOE, we have 4 different options, and in case of gold, we have again 4 different options with different methods of docking procedure. So we utilize multiple docking procedure, and we try to make sure that which docking procedure come up with the most sophisticated results. And so this is called benchmarking. We utilize this benchmarking, so we use gold, MOE, FRED, Autodoc, 4 different software and different software. And then we do the docking and redocking and then cross-docking, just to make sure that which software is more suitable in our case. We utilize this. This is long process, but what we are doing this long process just to make sure that at the end the shortlisted compound should be active. So at the end, when we are doing the experimental result, they should be the challenging. They should be accepted. So these are the things. So what we have done, and then in a pharmacophore process, so we start with 12 million compound, then we filter them, end up with a 3.4 million compounds, and then we apply the Likinsky rule, which gives us 6,000, around 6,000 compounds, and then we apply the pharmacophore screening, which gives us 6,002. And then we apply the docking procedure, which gives us the 15 compounds, and 5% on the result and 10% 15 compounds. These are the 15 compounds which at the end we pick up. So these 15 compounds we pick just to make sure that these 15 compounds are the, so these 15, and now we try to analyze these 15 compounds. We perform again MD simulation of 5 nanoseconds of all these 15 compounds, just to make sure that either these 15 shortlisted compounds really fulfill the requirement of the protein which we are expecting, which we are looking for. So they are really up to the mark, because we have the initial structure of the protein, we have the crystal structure, we know what are the requirement of the protein, and now the 15 compound, which in our understanding that they are the best. But you never know, because when you perform the MD simulation, we provide the aqueous medium for the compound to make them to find out the best orientation, then probably the orientation will totally change, which is beyond or out of the control. And when you can say, or initially we thought that these are the compounds should be very good, but after MD simulation we realized that these compounds are not good. What we have done, we performed MD simulation all this compound and analyze the result of each and every compound to make sure that the active site residues, which we have already pointed out during the initial study, they are having some connection with this small molecule or not. If they fulfill the requirement and they are as per the need of the protein, then we only shortlisted the compounds. So these are the detailed study of each and every compound. We can see the amino acid we have already pointed out in the initial study, the lysine, phenyl. So these are the amino acids which really should make some connection with the small molecules. We can see that these are the compounds which have good connection with hydrogen bonding and hydrophobic interactions with this amino acid, which simply reflect that these compounds should fulfill the requirement of the protein and can act as a good binder. So then in the next step, the model which we build from the QSAR will predict the activity of this compound. So these are the steps which we make a different steps just to make sure that our findings should be in a good direction. So what we have done, we predict the activities. So these predict activities are, again, you can see that these are almost 4 to 5 nanomolar active. So which is as per the standard of the compound. So we are almost sure that the predict activity is quite good. What is the next step? So we screen the compound, we shortlisted the compound, we predict the activity of the shortlisted compound. So this is a long process, and finally now we have almost 15 compounds in our head with their predicted activity. Now the step is to purchase this compound and to test them in the lab. What we have done, we purchase this compound, they are available from commercially available, and few of them are from our own database, national product. We hand it over to the our lab for the screening purpose. So these are our colleagues, they are performing this biological activity, they perform the biological activity, and then we coordinate the predicted activity, and this is the actual activity. You can see it is the 4.1 microgram to 3.6, 4.7 to 15.7. These are the three compounds which have a very good activity as compared to the others. So out of 15 compounds, 9 compounds are found to be active, and out of 9, 3 compounds are far near to the our standard. So we were quite happy in this case. These three compounds are ready to test them. So we so three compounds, and then we will in the process to these three compounds patent them. So we file a patent and we patent them, and now we're in the process to make a second step. What is the second step? What we are now trying to do? So these three compounds, we are going to make a library of this compound from computation library for more than 100 derivatives, and then we'll try to synthesize this compound in the lab to the next step. So they call the second step synthesis. So you can see there's a ranges from 5.7 to 4. These are the IC50 values we come up with the experimental results. And again, MD simulation really help us to understand which compound we should select, and then you can see the different steps from 1 nanosecond to perform the 5 nanosecond of every compound just to make sure that they fulfill the requirements. So over here, I think I'm on time, and next, still we have 5 minutes.
Yes, about 7 minutes. 7 minutes left. Yes.
Okay, that's fine. In 7 minutes, basically, I will skip a few slides, and so these are the detailed study. So what I would like to show over here, these are the detail of this compound. So you can say they are coming from the different commercially available database. So NCI is a database, National Cancer Institute. If you test this compound, this is free available, shortlist the compound, and then you can purchase this compound. So National Cancer Institute, they provide you this compound free of cost. You just have to pay the charges over there, the freight charges, so-called transportation charges, and then you can test them. So we have compounds. This is Cambridge database. We also have some compounds from there, and then we also have some database from the Zinc database. These are the compounds, and see similar activity we are performing a different target, but we never have the same results on a different target. That we cannot say that these are the hard and fast technique or these are black and white tools, and then you can apply the same technique for every target. Every target we have to come up with the initial, and we have every step we have to make sure that which technique is more suitable for this target. So that I would like to suggest all of my fellow that whenever you are trying to do any virtual screening, you have to make sure that don't follow any hard and fast, any black and white method. So you always try to find out which technique is more suitable for your target. The target is very important. Emphasize on target. Try to read your target as much as possible, particularly all the experimental aspect. You should read it before you are going to start. So theoretical chemistry, in principle, I should say that 60% on reading and 40% on reading. And if you will do the reverse of it, you will do the 80% of work and 20% reading. You can do a lot of information, and most of the time at the end you will realize that the result is not the mark. So better you spend 60 to 80% on reading and perform 20 to 40%. It is always to perform less but with accuracy. Accuracy, if you try to do some work with accuracy, you should have a maximum information, experimental information. So these are the different. We repeat the technique with a structure base, as I mentioned, and the structure base and then ligand base. And these are the details of this technique which I already mentioned. And this is my group mate. These are the wonderful team. They are working for me day and night on me, and what I'm trying to do that I try to collect a result from them and then try to publish them. So you can see what we are doing. This is the result of this. And this is my institute. This is called Panjwani Center. So currently I'm sitting in this lab. So this is first floor. I'm sitting in this lab. I'm talking side of this building, and this is the outside from the building, and welcome all of you to come and visit my institute whenever you have time. So this is another building. This is the chemistry part of our building. So as a whole, we call ICCPS International Center for Chemical and Biological Sciences. We have more than 25 buildings. Few of them are them. So this is the Panjwani Center where I'm sitting. This is the Satwal Center. So we have to, and I should not forget the funding agencies. We provide the different funding agencies. This is my director. This is Michael Lodi from Austria, which I started my computer from here. Rebecca, I visited him as a good fellow in Germany, Heidelberg, and this is from here. This is a very good partner, my full pride colleague. I visited him 7. Unfortunately, he is no more with me. Angela Wilson, I'm writing on the book, so called Frontier in Computational Chemistry. So we started with Jeffrey Madura. He unfortunately passed away 3 years back, and then we continued. Angela Wilson, we already have a 5-volume. It's already available. Frontier in Computational Chemistry. There's somehow my contribution in science. With this, I will thank all of you, and I hope if you take an happy one.
Okay, thank you, Professor Jahir. Please give applause to Professor Jahir. It is quite interesting theme about the computational chemistry. You know that in Indonesia there are so many like traditional medicine, and that we can also use it for everything here. So please give applause to Professor Jahir for the next presentation. But I think there is one question before we continue to the second plenary speaker. I think there is a photograph of the Rodi, yeah? Professor Rodi, yes?
Yes.
Okay, so you are apprentice of Professor Rodi. Okay, thank you very much again. And then we will have then, after the second speaker, we will have the discussion. Don't forget to write your question to the chat room or directly to the message. Okay. Okay, thank you very much. And we move to the second plenary keynote speaker. Then I call Professor, Associate Professor Dr. Warakon Limbut. Professor Limbut?
Yes.
Are you already there?
Yeah. Hello.
Okay, Professor Limbut, but not yet on the screen. Okay, that's quite nice. Okay, nice to meet you, Professor Warakon Limbut. Before we start with Professor Warakon Limbut, we would like to introduce about his achievement, his brief curriculum vitae. Professor Dr. Warakon Limbut is staff from Division of Health and Applied Sciences, Faculty of Science, Prin of Songla University in Thailand, of course. And he has already some academic qualification, his bachelor degree in chemistry in Rajabat Institute of Phuket. I think Phuket is quite famous, yeah? Okay. And then his master degree in analytical chemistry in Prince of Songla University in Thailand also, and his PhD in chemistry, in analytical chemistry also in Prince of Songla University. He has already so many publication and famous publication also, and he has devoted in analytical chemistry and also in forensic chemistry, yeah, Professor. Should I call you Professor Limbut or Professor Warakon? I don't know which one is.
Yeah, it's up to you. Both of them is okay.
Okay, thank you very
Both of them
much.
is okay.
Okay, Professor Limbut, I think it's quite easy to say. Okay, thank you very much, and I will please you for 40 minutes. Okay, 45 minutes for the presentation, and then we have the discussion for both of you. Okay, time is your, Professor Limbut.
Okay, thank you so much. So good afternoon, the chairman and all participants. I'm Warakon Limbut from Division of Health and Applied Science, Faculty of Science, Prin of Songkla University, Thailand. And first of all, I would like to thank all staff and Professor Amin Fatuni for giving me for the good opportunity to be a keynote speaker to share my experience in the electrochemical sensor from this event. Okay, so today I will give a talk in the topic of development of electrochemical sensor and their application on agricultural, environmental, forensics, and clinical analysis. Yeah, first of all, I think everyone might not know about our university, so I would like to introduce a little bit about our university. Yes, we have five. Pardon? Hello. Okay, so we have 5 campuses. This is Surat Thani, Phuket. I think everyone know Phuket. Trang, Pattani, and Hat Yai campus. The main campus is Hat Yai campus here. So I'm from the main campus. Okay, I would like to show you about a few minutes of our video from Faculty of Science. Is it for the good time? Maybe some student from your university want to join from the master degree or PhD degree in our university. So I would like to share some video a few minutes. The sound is it okay? Sorry. No.
Okay, quite nice. Okay,
Uh,
we can see clearly.
Okay, I think we have about the problem about the sound. Is it okay? So I will script it. I think maybe something wrong about my computer. Okay. So if someone want to know about our details, so okay. Yeah. Okay. This is the some information. If someone want to go to our university, Prince of Songkla University, please go to more detail in this one. Okay. Oh, sorry. Okay, you can go to for the more detail. You can go to here. Okay. For example, last 3 years ago, we have the good co-worker with USM Malaysia. Is it very nearby in Thailand? And then we have the good worker with the Professor Lim and Professor Chang, and we can produce or we can help each other, and then we are joined on the forensic side program until we produce like the first one. For example, this is the methamphetamine guy, Dr. Lee Khai. He is a methamphetamine guy, and he just finished from his thesis last month, and then he come to my lab, and then he developed the electrochemical sensor for detect the methamphetamine. That's why we call him the methamphetamine guy. Another student is that Kathleen. She is a Silacine girl also, and she developed a lot of electrochemical sensor for Silacine, and I will give to a lot of more detail for her. And then for her, Kathleen, she will have the thesis examination on October. I think she will finish her PhD thesis soon. This is for the just example. So if you are or your student want to come to join with our team or our university, please go to our website and then get more detail. Okay, one more thing that I would like to show is that this is our center. Our center name is Center of Excellence for Trace Analysis and Biosensor. We are focused on about the innovative sensor and sample preparation technology for light quality. So we did a lot. Like that's one, and we apply for many fields for food, environmental, medicine, agricultural, pharmaceutical, and forensic science also. And this is our activity. You can see we have a lot of activity during we work together. Like I talked to you, not only the research work, we are working with students, but also from the soft skill, that for the presentation, for the some innovation event, we also support them to go to present or show his or her innovation until we got a lot of award from our students. You can see. Okay, this is our team. We have the big team, and then we work together, and then we produce a lot of research work and basic research, and also the application, and also from the innovation. Yeah, the current research work from our tab COE. We are a lot of field. But for today, I will focus on electrochemical sensor. That's my familiar. Okay. For electrochemical sensor are an attractive option for agricultural, environmental, forensics, and clinical application because they're easy to use, simple, portable, fast analysis, and sometimes is it very high sensitive and low cost, and sometimes it can able to detect analyze without a little bit or no sample preparation, something like that. Okay, so the outline for today, I would like to present some the current our research work that we have been done, and we have been developed electrochemical sensor for forensics, environmental, clinical, and food and agricultural for today. So for today, I'm select our current that we have been published in the a lot of journal. So today I select from the 76 paper that okay, from 2019 to currently. Okay, yes, the first one I will go to the forensic analysis or forensic electrochemistry. Okay, actually the electrochemical sensor is not an official method for forensic science. However, we can develop or we can fabricate the novel sensor for use for in-house, in-house or lab build method. For what? If we develop for our lab build or in-house method, so we can use as a first test for screening to identify target, analyze for forensic evaluation, and then after that can go to the standard method, something like that. Did it? Okay, this is the research roadmap that we have performed for last time. Actually, the first one is that we got the problem or the pain point, the pain point from the stakeholder. In this case, we got from the Forensic Science Center 9. And then after that, we use our basic knowledge from electrochemical sensor, and then we need to put a lot of things from the creating. For what? We need to create until we get the new knowledge and the novelty statement of our team. For example, if we know that, okay, we want to detect some explosive, so we know the target analyze, and then we need to decide, okay, which technique that we will develop from the that target, and then so we need to think more. What is advanced material that we need to compromise in the modified electrode until we got the good selectivity and good the signal. So we need to perform on the analytical performance. We need to optimize. The first we will start on the optimization and then go to the analytical performance. If our technique is quite sensitive, so we just dilute sample and then test it. But sometimes it have a lot of contamination, or it have a lot of something that contain in the sample. So sometimes we need to develop more from the sample preparation until we get the good electrochemical sensor. Our target is that it used to be the screening method, simple, lab it, something like that. Okay. Yep. Okay. After we get the basic knowledge, so in this case, we also of course we got publication, we got the new knowledge, and in this case, we can we can submit the grant from the research basic, and after that, Actually, the normal people stop on the step 2, but not for us. We develop more because we need to solve the pain point from the forensic side. So we need to develop more to produce the prototype, and then we need to design more and fabricate more until we got the prototype and patent. I think in this case, if we have the prototype, this is very good for us. We use that prototype in our classroom. For example, I have a class on the forensic electrochemistry. After we produce a lot of innovation and the prototype, we use that prototype in our class. This is very good, and then the student also very happy because nowadays new generation of students need something is interesting, not just only the paper and just only the keep a talk. Okay, and our university, especially in my class, that I change I change the method from the teaching our student. Okay, after that we need to develop more until the user use it, and then they're happy about that. And that one, someone from company can license our innovation, and then finally, if our product go to the commercialization or go to the user, we are very happy, like I write that one. And also, actually, we not stop here. After we finish, so it will go back to the new project again because during the roadmap, we know a lot of people. So during that time we got a lot of knowledge, and we got up a lot of the problem that we need to develop more, something like that. Okay, so first for the forensic electrochemistry, I will show you about how to detect dark trace DNA, gunshot residue, and restoration of serial number, something like that. This is our current paper that we are published on the forensic electrochemistry. Become the first one. I think everyone know from the how to say, this is we develop electrochemical method to detect sibutramine. Actually, in Thailand, we are a lot of news that announced that a lot of product of slimming product put some sibutramine, and when we got the sibutramine, it will a lot of effect until if put a lot of things that it will be maybe dry also. Okay, in this work we develop electrochemical sensor to detect sibutramine, and in this work we try to modify porous graphene. Everyone know graphene, and then we develop more to produce the porous graphene to increase the surface area, and also you can see it's really good. One thermogram peak that we got, we can detect the sibutramine in illegal swimming product to 5 ppb. It is very low, and also we develop more until first one we know we have the basic knowledge, and then we develop more until we get the small device that contact with your mobile phone, so you can detect sibutramine in the slimming product everywhere. And this one we produce the paper. We use filter paper and coat the screen the graphene ink on the paper, and then use it from the electrochemical detection for sibutramine, something like that. And she got very very good award from the workshop from the National Research Council of Thailand. Yes, okay. Also another one is that the Yohimbai. I think everyone knows the Yohimbai. We got a lot of new from sick crime. Okay, there are a lot of side effects also, and then in Thailand also we have a lot of news. You can see, some people use from the bad guy use from the woman. And then, okay, so that's why we develop electrochemical method to detect Yohimbai. Yeah, okay, this is one also. We use caffeine also. And then also we develop more until, yeah, she also got the very good award, yeah, from the invention event also. Okay, every paper, you know, you can get more information. Yeah, maybe on the abstract, I keep the more detail. You can find it about that. Yes, another one. This is siloxane that, like I talked to you above, that we have good worker or with USM Malaysia, and then we develop more about the electrochemical sensor to detect a siloxane. Yep. Okay. And this one, yeah, this one also we use the we develop, you know, actually the skin pin electrode. If you buy on the market, it's very expensive, and then we need to create new strategy to develop or to fabricate the good electrode. It's very cheap. We also use the paper and use wax printer, yeah, to create the hydrophobic and hydrophilic region, yeah, and then coat the carbon ink or caffeine ink on them. Yep. Yeah, this is if you want to more details, so please go through that paper, and then we talk a lot of, we did cut a lot of them, and then you can see this is our electrode, and this is the reference of working and auxiliary electrode. Yeah, this is, yeah, okay, this is the paper. We use wax printer, you can see hydrophobic and hydrophilic region. Yeah, and also after we got the publication on the Journal of Pharmaceutical and Biomedical Analysis, and now we develop more. This is the quite big equipment. We develop more until we have like the handy drive, the small thing, the small piece of the handy drive, and then we can bring to everywhere. You just have the mobile phone, and we use our application, and then, you know, this is the paper. Yeah, this is the logo of USM. This work, yeah, we work together between USM and PSU. The student from USM come to my lab, our lab, and then did a lot. And she also have a lot of new knowledge. Okay, and this one also we say we submit to the Talenta. Now is it revised manuscript? I think it will accept soon. We hope. Okay, yeah. But because the question is not really hard, so we can answer it. So if you want to see about this paper, waiting about 1 month, okay? Yeah, another one is that actually this one we got the forensic give me the good problem. She said that, okay, during some people take the ice or methamphetamine in the morning, they will take clonazepam or alpha solam. So they want electrochemical. She said that she need the easy or the simple method to screen the people that take alpha solam or clonazepam or not, something like that. And that's why we develop more about that. Yeah, this one also we got the publication also in, I think, this year. Okay. Yeah, this one from the alpha solam, and another one I need to wrap up because a lot of publication. I wonder to show off you to overall. Okay, and this one also we develop more electro. This one we call adsorptive cathodic steering one-time method to detect the clonazepam, and now they develop more. You know, because this paper is alpha solam and this one the clonazepam. My friend said that, could you produce or fabricate the one sensor that can detect both of them? So now we develop more. I mean, we have one device, and then they have 2 slots. The one slot for detect the clonazepam, another one is the clonazepam and alpha solam, both of them. Is it very, you know, when we got the problem from the user, we are really happy, and then we quite quickly to develop for them something like that. Okay, this one also we just published this year, and we developed electrochemical sensor to detect atropine. Yeah, this girl, yep, very, she also helped me a lot. Yeah. Okay, Everyone hear me a lot. Okay, this is we develop adsorptive anodic spin-1 chemistry for detect atropine in urine. Okay, this guy now he's a Dr. Yatisak Ponsuwan. We are develop electrochemical sensor to detect promethazine. Yeah, almost paper that I will that we have been done. Is it drug abuse? Yeah. Okay. Okay, we develop more. This paper is very high. The impact factor is very high also. And then this one is it we synthesize. Yeah, before we synthesize the nanoparticle that that code on caffeine nano pellet. Yeah, this one we show that we use the this composite, and then we use nanoparticle to electrocatalytic from the promethazine, and we can detect, not only from the drinking water, but also in your urine sample also we can detect it. This one also is Dr. Suparat or Dr. U. Yeah, she also very good student, and she have a lot of paper also. This is we also develop the electrochemical to detect the hydroquinone. Hydroquinone. Actually, in Thailand, we don't allow hydroquinone that contaminate or contain in the whitening cream. But also we got a lot of hydroquinone or mercury in the cream. I mean whitening cream. Yeah, this one also. And okay, after we got this paper, and then we develop more. And we want that we need to develop more to until we have good LOD or IOQ. Yeah, in this one also we use the polyphenolate. Is it this chemical? Is it very very normal in our lab? Because this is touch indicator, but we develop more on the surface of the electrode. Yeah, this is very good also, because we can fabricate, or we can fabricate like the microstructure of polyphenolate on the working electrode, and then we use it to increase the surface area, and also act the adsorption to detect the hydroquinone in the whitening cream. This one also very good. And also nowadays, when we got the new knowledge, and then we move. I mean, we got the condition, like for this one, this paper and this paper, we got the condition to use like the concentration of buffer, pH, and everything. After we got it, and then we miniaturize. We miniaturize from the big system go to small system, just the one card. So you can bring this card to everywhere, just like that one. This is like the ATM card, and then we also develop the electrode in our cell. It look like it's very 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 small. Okay, and one more thing. This is the paper. Yeah, okay. The Dr. Suparat working on them. Yeah, we develop electrochemical sensor to detect trace level of DNA. This one we got we got from the forensic police also. They say that in the car. I wonder to know how, okay, the amount of protein that inside in the car, how much is it? Because they want to know the amount before they take that sample to working on the real-time PCR, something like that. And then actually they say that they use the nano dot to detect amount of protein. So in this case, we develop the electrochemical sensor. Yeah, not only electrochemical detection, but also for the extraction, we use iron nanoparticle. Yeah, we use methylene blue to separate or extraction DNA from the sample first, and then we detect it by the electrochemical sensor. This one also is very good impact factor for this paper. Another one is that this is very good also. Yeah, this one that this guy, he developed the electrochemical sensor to detect zinc in the human similar fluid. Yeah, this is very good work also. And then we take a lot of sample from, a lot of sample from the human similar fluid and compare with the standard method, and the result is very good. It's really relative between each other. Okay. And one more thing about the electrochemical technique or electrochemical sensor for applied to forensic science. This is the nitride amperometric sensor. Yes, we developed. You can see, develop until we got, this is quite big in the beginning. You know, we have the pump, we have the force cell, we have the electrode. So you can use every electrode that you have in our system, and we have monitor. Yeah, something like that. This one is really good paper also. And also, you know, we develop more from the big one. This is not too big, okay, but we need smaller. That's why we develop more until we got the smaller one. And this work also we got the big award. Yes, we got the Excellent Innovation Award from the NRCG, and we got the gold prize in Innovation Award. Yeah, this is we are very happy after our student got that one. You know, this is my very happy. Okay, I would say. Okay, nowadays we are developed to the smart nitride sensor. You can see, I think maybe next 2 years, forensic police in Thailand. If it's work, okay, they can bring just only the card, and then go to the field, or some people that already use the gun, so we can know amount of the nitride. Yeah, okay. One more thing, okay, because limited of the time, I need to quickly to talk. Okay, one more thing that from the electrochemical technique, this is very simple, very simple thing. I think everyone know reduction and oxidation, right? And then you know what happened, how, okay, how we produce the very simple way. I mean, from the reduction and oxidation, until we got the innovation to help and or use from the forensic side. Okay, like this one. Okay, we are developed the novel electro etching and plating device. So what is the PE pen? I call PE pen. P mean plating, E mean etching, and pen is it the pen? Okay, I this is because the limitation of the time. I need to show some video. This is I would like to introduce about PE pen first. PE pen. I am a pen. I want to pen. Painting pen. I want pen. I want to etch. Etching pen. Painting pen. Etching pen. Etching painting pen. PE pen. Yeah, I think everyone enjoy about PE pen, right? Yeah, behind of PE pen, you know, we have a lot of things behind PE pen. You know, PE pen, that mean P plating or etching pen. Yes, you can see we have the pen, and we can use for plating and etching. Okay, I will show you this one. Yeah, this one. Yeah, this is the pen. We can use two mode, plating and etching. This is okay. Our event that we are go to the some event, and then the student enjoy about our innovation. If we want to plating, so for example, this is the gold plating, or if you want to etching, so you can etch the stainless. Yeah, it's really good because of limit of the time. So sorry, I will go to quickly. Yeah, this is our product. You can see we can play the gold on the ring, on everything. And this one also, last time I have a chance to go to Indonesia. Yeah, York, Jakarta University. This is the production of the student from that one. Okay. Yeah, you can see. But this is just only etching and plating according to reduction and oxidation. Reduction, that means, okay, we use from electroplating. For the oxidation, we use for the etching. Okay, so it's very good, very good that we can use just only the salt, sodium chloride in your home. Yeah, the sodium chloride, just the salt, and then use our pen to plate. Yeah, it's very good. Yes, and then we apply from the forensic side. I would like to show like that. Normally, the forensic side, if they want to recover the serial number, though, so they use the chemical etching. But we use our just only salt, so sodium chloride, you can see, and then use our pen go to this mode. We need to go to the etching mode. That means this is the positive, this is the negative, and then we just actually inside on the pen we have the sodium chloride also, and then we need to paint this area. Yeah, this area is the positive. The oxidation reduction will occur here. That means it will etch this metal, something like that. Yeah, this is the real thing that forensic police use. Our innovation, you can see this is before and it is after 776S 0S something. I think you can see. Okay, this is not only the pen, but also, you know, if we want to use from the big car, the track, something like that, we need to use the big equipment. And then we also use the app. You know, nowadays the forensic police use some application. You know, we have app to apply the potential. This is the real student that police use our innovation. Yeah, this one also you can see. Yeah, this is from the chassis of the car. This is before. After, you can see 7, 3, 8, 6 something. Yes, a lot of things. One more thing, you know, in Thailand, use our innovation. You can see, this is will make the researcher very happy, you know, because of our innovation that we send our innovation to the user. The real user use our innovation. You can see, just really simple just really simple knowledge on the redox reaction. Okay. Not only from the etching, for the printing also we use that one to, you know, to find the fingerprint detection, something like that. You can see, yeah, a lot of things. We just writing the manuscript, so if you want to see, so waiting a few months. Okay, I would like to skip that one. I think everyone know inside in deep our innovation that I try to show you on the picture. And also, this is just only the first forensic side. Okay, I will go to the next one with the environmental. Yes, Dr. Kitisak also developed more about this one. We developed electrochemical method in the flow system to detect hydrazine in the wastewater. Yes, okay, and you can see we develop more. We use the P dot to coat on the gassy carbon sphere first, and then palladium nanoparticle will be deposit or what fabricate on the surface of the gassy carbon sphere via P dot, something like that. Yeah, we got, yeah. This is very good program. You can see, is it really fast? We can detect, like I would say, 1 hour is more than 60 samples, something like that. And this is very good. This is the result from the wastewater from everywhere, and then we compare with standard method and also the code recovery. Okay. And also this is Dr. Supatini. Okay, three of doctor just finished this year. I am very happy also.
So,
yeah.
Sorry, Professor Limbut, for 5 minutes left. Sorry, just
5 minutes left.
5 minutes left.
Okay, I have 5 minutes left. Okay, this is okay. This is from the okay. We developed this one from the to detect free chlorine. Yes, on the swimming pool. This is very good also. Yes, I will go to the clinical analysis. This one also develop electrochemical sensor. This one we produce electrode in our cell also, and then we apply them from the to detect paracetamol. Okay, this is very good also. This one also we develop electrochemical sensor to detect hydrogen peroxide in the similar human fluid also. Yeah, this one also we develop electrochemical sensor to detect dopamine. Yeah, I think everyone know for the Parkinson. Yeah, we can detect it by using electrochemical sensor. And this one, not dopamine, but also the glucose detection we also develop. Okay. Yeah, and then we develop more from the very portable electrochemical sensor to detect the glucose. Okay. And this one, okay, not like before that I showed you, is it just only one sample, but also in this work, we develop electrochemical sensor to detect 3 analytes at the same time, which is glucose, yeah, uric, and dopamine at the same time by using the dual working electrode. And we also got a lot of award from this work. Yeah, this is a step that we develop. Okay. Yeah, one more thing that we develop electrochemical detector to detect iodine in urine. Yeah, this guy is a very good guy also. Nowadays, he go to do something on the market. I think he will list. Okay. Yeah, this is the work from the Dr. Suparat also. We develop electrochemical method to detect 3 types of tumor marker at the same time. You can see. Okay. And also we got up the big award from the NRCT also. Yes, three award at this event. Yeah, the last one from the food and agricultural. Yes, this one we developed electrochemical sensor to detect column physical. Yeah, and we develop more from this work. Go to like we use aptamer, and then we develop more like the portable apta sensor to detect the antibiotic. You can detect column physical. You need to select the electrode like the green one, or if you want to detect the nitrofuran, you need to use the yellow one, something like that. And this guy is a very good guy also. Yeah, he got many awards also. Yes. Okay. Another one is that from the chili. I think everyone knows chili. We are very happy when we take the chili, but this one we develop electrochemical sensor to detect capsaicin on the chili. Yeah, this one we have the hardware. You can see the hardware we develop. It look like the very good thing that is it look like chili. This is our device. Yeah, and then we have app also. Okay, yeah, is it very simple one, and this paper is really good also, and a lot of magazine all the world have been announced or have been put about this one on the news also. Okay, and also he got the excellent innovation award from NRCT also. Yeah, nowadays this work the company already licensed it, and then nowadays we are develop like we try to develop together to be the smaller one and very cheap one, and hopefully for this year or next 2 years, this work it will go to on the market. Okay, yeah. Not only electrochemical sensor, is it the last one that I would like to show to you? Is it we just got the publication on the food chemistry. Yeah, is a really good impact factor also. We just use the simple one or the simple method to develop more to detect, ethanol. Yeah, ethanol from the baby mango, because if we keep a long time, they produce the ethanol. So is it very good from the Muslim? Because if the food have a lot of ethanol, is it how to say, is it not good for Muslim people? Yeah, that's why I developed that one. Is it developed like that? You can see it can. This is the we call smart sensor. You can put on the lift or the container. So yeah, this one also we got the good award from the NRCT also. Yeah, That's all that this is outline of my talk. I think a lot of work that we have been done is it good for all of you to know about our team. Yeah, which one what thing that we have developed or we have been done before. I think okay, our electrochemical sensor it become to be the new draw in agricultural, environmental, forensic, and clinical analysis. So finally, I would like to thank our sponsor. Yes, okay, a lot of sponsor, Prince of Songkla University, Faculty of Science, TAP, COE, PERCH, ITJ, PhD, Master Lab, NIU, TRF, Forensic Forest, and the University and what NRCT. And also, I would like to thank my family. This is my wife and my two daughters. Okay. And also, I would like to thank our member. Yeah, this is our member. Every time we go to on the field or go to everywhere, so we work together. Thank you for their help, a lot of things. And also, this is I would like to show about the thing that we have got after we work very hard on them. Okay, and this is some award. Yeah, some award that we have been done, and we like talk to all of you. For me, I'm not only the lecturer, I also the supporter. We need to support our students to learn more, not only the hard skill, but also for the soft skill. We train them, we support them. Yeah, go to every event that I can send them. Okay, and we got a lot of award from a lot of event. Let's see. This is just only our team. You can see for each event. Yes. Okay. Thank you so much. I think the time. Yeah. Okay. It's still on time, right? Sorry.
Okay. Thank you very much for Professor Limbut. That's quite a nice presentation. Yeah, you using such kind of electrochemical method for make some kind of sensor. That is quite nice. And one question for you before we continue for discussion is the actor on the video is you? Is really you?
Pardon? Sorry.
The actor on video who dance is you dancing. Yeah. It is you? Someone who dancing on your video is you?
Yes,
someone,
me.
Oh,
me. That's me.
Oh, that's quite nice. It means that you are.
Sorry, I think Amin no. Professor Amin no. Yeah, because
you are scientist and dancer also and jokers like that. Okay, thank you very much. Very interesting. For,
yeah,
yes.
A lot of videos. Yes.
Okay, thank you very much for your presentation, nice presentation. And I would like to have discussion. We have about 20-minute discussion for both of you, and we can begin from question from Professor Dr. Zahir Ulhaq Hasmi. And of course, before we start discussion, please don't hesitate to write the question, or you can raise your hand. Perhaps I will give a chance for someone who raise hand as a like priority. Okay, if someone want to raise hand or directly ask the question, I think that's quite nice. Is there anyone? Okay, perhaps still need time. Okay, I would like to begin from the first question. Come to Professor Dr. Zahir Ulhaq Hasmi. The first question from Yan Habibatur Rohmah from Unsud. Yeah. In analyzing a drug, it is important to ensure that the drug is on target. I think there are so many questions. But how to conventionally ensure that the drug design is right on the target while in the partitions body, does it need additional research outside in silico to find out? Find out the solution, of course. And besides being able to determine the biological activity of the drug with user, yeah, can we also know computationally the possible set effect of the drug when it hits the target? Okay, I think that's so many questions, perhaps repression so many audience. Okay, please, Professor Zahir, time is due. I think first question.
Okay, thank you for the question. So I would like to answer the question. Okay,
sorry. I think from Professor Zahir first. Sorry.
Okay.
Okay. I will give the time to you, Professor Limbert. But I think the question to Professor Zahir first. Professor Zahir, are you ready? Hello? Hello? Oh, okay.
Not yet.
Not yet. Okay. I think we move to firstly to Professor Limbut. Yeah. Okay. Okay. Please. That's not from the committee. Okay. It is from Jufri, Diponegoro University. Want to ask you about Professor Limbut. The sensor being produced mainly for the analysis of the medicine. What I'm asking is the decision that you produce, how accurate is it is to detect, and can you describe again the reaction that occurred between the material you use with the drug? I think first question, Professor Lindo, please.
Okay. Okay. Sometimes the sound, I cannot hear from you. Okay. Yeah.
sorry.
No, it's okay. So I can read it. That's one, right? Okay. This is the question from the
Jufri.
Okay.
Yes.
The first one is that. No. Okay. From our work, actually, from the one in the electrochemical sensor that apply from the medical analysis. Actually, is it very hard from the commercialization, but in the beginning, after we got the very good, the very good performance, and then we try to nowadays a lot the company, like I talked to you the last slide, the company, the name of company Master Lab. The Master Lab want to license our work, go to the commercialization, but also we need to develop more to each other because of, for the medical analysis, we need to perform a lot of things, like for in Thailand, we need to send a lot of document to the government, like we call OYO or something like that. And then, for my work, actually, from the if the work from the medical sensor nowadays is not go to the commercialization, but we still put a lot of work until our work go to the commercialization. And for the accuracy, for the detection, actually for the accuracy, we work with the hospital. That means like for glucose or dopamine or some tumor marker, we work together with the hospital. We have the one sample, and the hospital use the same sample to detect by using their own method, and our electrochemical sensor also we use that one, and then we compare the result together. And also not only compare that one, but also we check the percent recovery, or we did a lot of the analytical performance until we would say that our sensor is very good accuracy. Sometimes some sensor is not accuracy. Some sensor we need to put more sample preparation. For example, for the glucose, sometimes we need to put the membrane. I would say the plasma separation membrane on the top of the electrode. For what? For avoid or eliminate some protein or some red blood cell from the sample. go to our electrode, something like that. And some work that we need to compromise our sensor with, sorry, yeah, we need to compromise with the microfluidic sensor. I know microfluidic technique for sample preparation. Our sample, yeah, before go to the detection. Yeah, okay, can you again reaction occur between material? Okay, yeah, actually from the dark detection. Okay, if from the dark the detection that we have been developed. Sorry. Yeah, that we have been done is that we before we are fabricate or we are modify electrode surface, and then we need to study the electrochemical behavior. Sorry, this is a lot of time that they could. Hello,ครับ Hello,ครับ
You still on mute, Professor Lindu.
Okay, sorry. Okay, from the our method that we have been developed. Okay, first of all, after we are modify our electrode, and then we need to have a look, or we need to study or more detail on the electrochemical reaction on the electrode surface. For example, like the from the sibutramine. Yeah, we need to know the structure of sibutramine, and then we need to know our material that we modify, and then we need to study more for our study. So we need to find out the literature review about that drug, and then after that we need to develop to study a lot, like for example cyclic bond geometry, and we need to study the impedance about a lot of things until we get the mechanism, how many electrons that occur on the electrode surface. Is it oxidation or reduction, and how many electrons that occur on the oxidation part, or how many electrons that occur on the reaction part. After we learn more, or we know, we got the new knowledge from the electrochemical property of this drug on our modified electrode, and then we develop more from the sensor, because we can see for the electrochemical sensor, we can fit the potential that appropriate or suitable for the analyte that we want to detect. Is something like that. Is it clear? I'm not sure. Sorry, the telephone disturbed a lot of times.
Okay, no problem. I think that's quite okay for this time. Perhaps there is any further question, Mr. Jufri can directly write again. Okay. I think we move turn. Please, the committee change to the Professor Zahir Kasmi, please. Okay. It is the question from Habibur Rahman. Perhaps I have already read it, but okay, Professor Zahir would like to directly answer it from the first question.
Yes, Habib. I mean, he is computationally ensured that the drug design is right on target. In principle, when you are doing computational techniques, fortunately, you have multiple options. So what we can say is a control test. So you perform one experiment computationally, and you perform the another experiment on parallel, just to make sure that your result is reliable. So you can, for example, in my lecture, I can show you that we started on a structure-based, drug design-based, and we use more than one protein target. So what you can do exactly, you can perform a number of experiments at a time, just to make sure that the results or the outcome of all the results should be just similar. Then you can make sure that you are. And then you ask, bioregular drug with QSAR, can we also know completely the possible side effect? Yeah, definitely. For side effect, you can perform another test. This is called QSPR. So you can perform it, which basically tells you the impact of your compound on different factors. For example, the solubility, the side effect, the things like that. You can also perform these things. And there is a very established method is already available to perform it. So most of the commercial software, for example, this MOE, already come up with these techniques and you can perform.
Okay. Thank you very much from your suggestion and your question. Yes, actually, when we are develop the drug, electrochemical sensor to detect drug, actually, the problem that we got from the forensic police, they say that I would like to know in the drinking water or the juice or the apple drinking water, they contain some drug or not. That's why in the beginning that we are developed, and our sample is also detect the amount of drug or that contained in the drinking water. And also actually is a very good thing that if our method can apply from the human. Actually, I know is it not easy, but nowadays we have the knowledge, so we can go to more detail about the partial body or something like that. Like you say. But and also for the computationally, actually we are not familiar about that. I think I know you are familiar on them, so we can work together. Maybe you can simulate the molecule and the one that actually for my sensor we have two things. The first thing is that the target analyze. The other thing is that the composite or some material that can select to the target analyze. Is it a very good time to meet together? Maybe you can decide for me, and then so we can get you work on the simulation or computer combinational, and then for me I can use from your information to working on the experimental thing, something like that.
Okay, I think
Exactly.
I think that's quite nice. Both of you can collaborate together, and I think you can combine between Professor Zahir and Professor Limbut about the theoretical and then for the application. Okay, then I think Professor Limbut, I would like to move to question to Professor Zahir again. Professor Zahir again. And then we move to question to you, Professor Limbut. But firstly, to Professor Zahir, it is question to Professor Zahir from Vida Permata Wirasti from Unsud also about what are the requirements for the protein that we want to docking. I think that is for the beginning knowledge, but that's quite nice question.
That's very interesting. What are the requirements for the protein? Normally, in principle, when you select a target of the protein, that, for example, I'm interested to work on cytokines, or I'm interested to work on kinases, or I'm interested, whatever the target you select. Once you select the target, then you go to protein data bank and you type your target of interest and you come up with a number of solutions, which I explained in my lecture also. Now, the selection of the protein is very important. Which protein I should select for my purpose, because normally in protein data bank you can have more than one option. Then you have to see the protein which comes in or deposit in the protein data bank. You have to read the experimental paper, all of them. What are the techniques used to establish the 3D structure of the protein, and then you normally try to get the best structure with a minimum interference, minimum mutations. So you have to see there should be no mutation, there should be no additives, there's things like that. So one by one, of course, 5-6 points, which I already explained in my lecture. So you have to see the 6 lecture, and then the last but not the least, the most important thing, the resolution. The protein with the maximum resolution, you should try to use this protein, and then the entirely solve structure. So these are the few points you have to make sure that this is the protein which fulfill all the criteria, and then I will select this protein for my further experiment.
Okay, thank you.
I think it is nice question also. And please, committee change to the question for Professor Limbut. Okay. The first question already done, and then the second question from M. Khalid Junaidi. I start research using potentiometry for electroselective ion cold EU for just 1 year. My actual suggestion about that is potentiometry still give prospective method for AC electrode selective ion because the limitation of our apparatus and our lab. I think okay, limitation you need money, of course, but no problem. But this is okay. I'm Khalid Junadi. Thank you very much. Please, Professor Limbut to answer the question. Nice question, Ivan.
Oh, okay, for question number 2, right? Yeah.
Yes.
Okay, sure. Yes, I think, yeah, actually, the potentiometric method is another way of, another method from electrochemical method. So nowadays, in our lab, we use just only the emperor. I mean, we didn't use the potentiometric because, you know, yeah, I know this is very good, this is very selective, but also it's very expensive from the membrane. We need to synthesize, or we need to buy a lot of membrane that is selective to the target analyte. Yes, yeah. Even though they are very selective, right? But yeah, it spend a lot of money also, and also, yeah, I would say, in my lab, we are familiar on the one-time program than the potentiometry. Yes, because even though this method is selective, but also we know sometimes that the membrane, yeah, when we prepare one time, you know, if some protein or something broke on the membrane, it's also we lost electrode also, and then it's not easy to recover. I mean, to renew electrode. But for the one-timetry, we can apply the potential for the cleaning step. Like for example, before detect the neck analyte, we can apply the potential like 0.5 volt for few minutes for renew surface, and then use them it again. Yes. Okay. Potentiometry is very good also, I would say, but I'm not familiar on them. I would prefer on the one-time metry. Okay. Yeah.
Okay. Thank you very much. I think I think that the second question is usually you using like classic carbon, static classic carbon, or with rotating disc. It is just a simple question for you. I mean, usually you need classic carbon, yeah?
Yes.
Yes. You usually using static classic carbon or moving, rotating disc electrode.
No,
I mean.
no. Actually, because of rotating. Okay, I know. I get the point. Yeah, the rotating electrode is really good also because they can avoid the diffusion of blah blah, a lot of things. But also in the lab, we just use only the just calcium carbon and skin pin electrode because our focus is that, yeah, for the future we will apply or we will transfer our knowledge go to the commercialization. Yeah. I think for the rotating electrode, is it work? Is it very work or worth from the, if we want to study some electrochemical property?
Yeah,
on the electrode, is it very good? That's actually very good, I know. But yeah, actually we didn't use it from my lab. We use we use that's only the static one. Yes.
Okay, I think that's quite nice. Even you have static, but you have some paper. I think that's quite good impact factor also. I think quite nice. I'm salute for you. Okay, I think the third question is just intermezzo from me about the question, and then the third one from Roy Andreas, Mr. Roy Andreas from Unsud also. I think he said a very interesting presentation. I have a question for you. Is any special criteria for chemical material to get a good sensor? It is requirement for material for a good sensor. Okay, please, Professor Limbut.
Yeah, again, please, because the sound is not smooth for me.
Okay, you can read the third question. You can read it in the third question.
Third one. Okay, the third one. Okay, that okay. Can you hear me?
Okay, that's nice.
Okay.
We can hear.
Is any special criteria? Yes. Okay. The criteria of our sensor to be go to the good sensor, right? Okay. In the first one we need to know what actually we need to know what is the target analyte. If we know the target analyte, and then we need to find it more which nanomaterial that's suitable for us. Yeah, first of them we need to find it out from the literature review. Okay, how many paper that in the previous work that have been performed, and then we need to read a lot of things, a lot of paper, and then we need to find it out, and then we need to create more until we got the new one that not the same that the some paper that have been published before. Like for example, like for example from the last one that we just published on the electrochemical method for detect hydrogen peroxide in the similar fluid. Yeah, in this one, we want to use the palladium nanoparticle, and then we need to code on the gaseous carbon sphere. Gaseous carbon sphere is around 5 micrometers. Yeah, this one is very small. We use them from the enhance the surface area and conductivity, and also we need palladium nanoparticle deposit on them. From the previous work, we just deposit directly, and then we think it more okay. But in previous work, is it not stable? Is it not stable because they just I mean palladium nanoparticle just deposit on the gaseous carbon sphere, and then we need to think it more okay. How many chemical that can coat on the gaseous carbon sphere? Yeah, but the chemical that should be high conductivity, not low conductivity, because if we coat something that low conductivity, the sensor will lose the sensitivity. Yeah, and one more thing, that chemical is supposed to be act as a support to be let the palladium nanoparticle grow on them, something like that. Yeah, this is the criteria that we use the chemical material for the sensor.
Okay, I think quite clear of the answer of you, and because we have just limited time, please move to question to Professor Zahir. Okay, before we started, I think the second one not yet finished. Yeah, please the second one, number two question not yet done.
Number 2.
Okay. Number 2 is already.
Already, yeah.
Already, yes. Please, okay, number 3, please. From Poncho, Mr. Poncho from Untitled also. I want to ask to Professor Zahir, in your opinion, what is the most powerful, user study or molecular talking? Please, Professor Zahir.
Hi, Poncho. I mean, this is very nice from you.
Oh.
In principle,
Right.
it's in principle to compare the QSL molecule docking is just like comparing a banana and with any other fruit. So there's two different techniques, and the output is totally different. Normally, QSL we try to understand, utilize it to predict the activity of any compound. For example, even if you would like to predict the weather, you can go for the QSR or similar life. So if you would like to predict the nature of a human being, predict of anything, so this is a prediction. The QSI is a prediction technique. You would like to predict the unknown thing which has never been tested. And if you are talking about the docking is normally to understand that thing. So if you have something in your hand, now you would like to understand in detail. So this is molecular docking. So there's two different techniques, and you should not compare with each other. And the next is, I hope this is clear for Poncho.
Okay, thank you very much. I think you know each other, yeah, Professor, and I think both of you is the expert on computational chemistry or talking, yeah. Okay, you can discuss after that. Okay, and then I think the number 4 from Mrs. Riana Ningsih, what factor affect the success of talking a compound, please?
This is very interesting and very logical question. What are the effects that success of docking? If you're talking about the docking, though, as I also mentioned, that the most important thing is the knowledge of experimental knowledge. So if you're trying to dock any compound in any target, you should know the structure. You should have very good knowledge, depth knowledge about your target. If you have no knowledge about your target and you are just going for talking, probably you will go some rubbish result. So target information is very important, number one. And then number two, if you are going to do talking, then you have to know the which are the cofactor and the items which I should keep it and what I can delete it from the molecule before starting talking study, which you only know about the target. If you know the target, then you can do. For example, the water molecule, I should remove them, I should keep them. Some cofactor, I should keep them, I should delete them. So the most important thing, you should have the knowledge of the target. So
Okay,
before
okay. Thank you very much. That is, I think this enough. I think next question move to Professor Input. I beg for the committee to have like I think five-minute extension to answer the question to Professor Limbut, please. The next question is from Wulan from EPB. Currently, we are working to develop electrochemical sensor, but still in basic stage. I am very interested with the printing technique for electrode fabrication and also for the detection process using mobile phone. Would you please give me more explanation about the printing technology and also about transducing technology using mobile phone? I also will be very happy if you could allow me to send you email for further communication. Okay, I think the question for you, Professor Limbut.
Okay, this one for me, right? Okay, sorry, I didn't saw too much. I confused in the beginning which one that answer for me or answer for another person.
There is so many questions.
Yeah, I just got it. Okay, this one answer for the question.
No, I think would you please give me more explanation? I think about the printing technology.
Okay,
and the printing technology. I think this one.
Yeah, the printing technology. Actually, we have a lot of technology that we use in our lab, and the one that very familiar for us is that we use the wax printing, and also we use screen print electrode. Nowadays we have like automatic and the semi-automatic screen print electrode in our lab. Yes, that's it. The question is that what is the technique from screen print, right? Okay. Yeah, we use print wax printer and screen printer electrode in our lab. Yeah. For the detection process using mobile phone. Okay. Yes, actually, yeah. Normally, actually, we use actually nowadays the potential state that available in the market, there we can use the mobile phone and also from the computer. So you can use both of them, and also we can build by yourself. Like for example, this is the card in Thailand that we are developed. Oh, I don't know. You can, yeah, this is just really the one card. Yeah, this card, we can use the mobile phone that we have the we can contact with our mobile phone, and then but also we need to writing the software. Yeah, we have the team to writing the software to control the applied potential, and also a lot of things. Yeah, for the application, something like that.
Okay.
Yeah, maybe if you need more detail, please send the email to me. Yeah, maybe we can talk after this. Okay.
Okay, thank you for nice offer about this further communication. And perhaps I'm also interested also because I just buy potential start or galvanic start. I think that's why I asked about the rotate of this electrode. I think that's quite nice. And is there any extension time? Committee, please answer me. Or whether I have to stop it or okay. Stop it
Yes,
or
please.
again?
One more question is okay.
Okay, one more question. Okay, because there are so many questions for both of the expert. Okay, one question. It is from Faisal, Mr. Faisal from IDB. I would like to ask Mr. Warakon. Most of your research used graphene or graphene nanoparticle as sensor material. I think quite nice. What I'm asking is, Besides the role of graphene provide good electrical conductivity, can the graphene maintain the stability of the sensor? Because I will work in the electrical sensor using MOV, but some articles said that MOV not really good in stability. Thank you. I think that's quite quite nice question, because I work also in graphene. I would like to hear from you also. Okay, Professor Linwood, please. Professor Linwood, or if you don't really hear,
Okay. Okay.
you can read it directly. Number
Hello?
5. Hello, yes.
Okay. Yeah.
Hello.
Hello. Yeah. Okay. Mob is. I think it's mob is very good nowadays because mob is in a lot of researcher that use mob for the modified electrode. Yeah. I know some people say that something is not good, something is good. It depends on them. If I use mob, I also say that mob is really good. Yeah. I think it depends on your presentation and your create your work. Like for example, if you use morph and then you compromise with something more until they got the more function. If you got more function, so the stability is you find a very good stability, and you get the good electrocatalytic blah something like that. I think every material they have the both sides, the good thing and the limitation thing, but it depends on our thinking and our writing. So we need to defend our work, and we need to keep. Okay, some papers say that when we are writing the manuscript, and we got a lot of comment from the reviewer is that you say just really the good things. What about the bad things? Or what about the limitation? So that's why, yeah, we need to writing more about the limitation of the modified electrode. Yeah, for my opinion, graphene, carbon nanotube, MOF, or carbon bag. Now they have a lot of things come. So yes, I think it depends on us. It depends on the researcher. Okay, this is my answer. Thank you.
Okay, that's quite nice and diplomatic the answer. I think very interesting discussion for both of you, Professor Zahir and Professor Libut.
I think the last answer is very logical, that whenever you are using something, you can defend it, and if you are not using it, you cannot defend it.
Yeah, yes,
like it.
Yes, that's true. Okay, thank you very much, and I would like to give you both of you applause before we giving certificate. Please applause to both of you. Very nice discussion. Even the time is not enough, but you can follow the further communication or something like that for both of the expert. And then we move to the next session. I would like to give you certificate for both of you. I think firstly for Professor Zahir. Okay, thank you very much for the your presentation. I think this certificate is for appreciation of your coming in this virtual conference. Thank you very much for the nice knowledge for us. I think I hope this certificate just to memorize if you already here and with us in this GCC conference. Okay, thank you very much. And then next, to Professor Limbut, I would like to thank you again for your coming in this virtual conference, and also this kind of your knowledge is quite quite good, and also with your dancing also. This certificate is also for your dancing, yeah. Okay. Okay, that's quite nice. Okay, one again applause for both of you before we move to the MC. Okay. Thank you very much, and I'm Akmanto Herwibowo from Universitas 11 Maret. Perhaps Prof. Zahir know Dr. Fajar is our colleague from my university. Yes, and I'm sorry if we have some kind of not nice talk or speaking, I would like to sorry to all of you. Okay, thank you very much, and wassalamualaikum warahmatullahi wabarakatuh, and please your time for MC.
Thank you very much for you and for the entire team. I know a lot of people are working on the background of this to make it successful. I don't know that everyone and cannot say the name of everyone, but I really thanks for everyone from the depth of my heart for this wonderful event and wonderful platform to discuss with each other. And hope we will see us again sometime in near future.
Okay.
I'm sure.
Thank you.
See you. Okay. Bye.
Bye. Bye.
Bye. Monggo, Mbak MC silahkan.
Okay, thank you so much for Mr. Atmanto Wahyu Wibowo for guiding us in this plenary session and delivering certificates for our speakers. And now we are moved to the prayer and break session. So for all participants, you can take a break and pray, but please don't leave this room because we still have the session, parallel session at 3:30 p.m. So thank you and have a nice break.
Nice break.